Over the last 3 episodes, we built a RAG system, an agent platform, and an inference service. And all 3 of them reach for the same store, a store that finds similar content by meaning. RAG scoops the relevant passages out of it. The agent uses it as long-term memory. This episode, we crack that store open. The vector search system. Say the words vector search, and it sounds like more AI wizardry. But take it apart, and the part that's actually AI comes down to one line. Turn text into a string of numbers. That's the embedding. Everything else is an old database problem. It just swaps equal for close. Cut through all of it, and it's just a specialized database. An ANN index, a scatter-gather shard layer, an LSM update layer, and a query planner, all wrapped around that one embedding function. First, let's be clear about what it's supposed to do. Given a query vector, find the handful in the store that sit nearest to it. And that word nearest needs a line of explanation. The embedding lays the meaning of a piece of text out as a point in high-dimensional space. The more alike the meaning, the closer the points sit. So find related content turns into find the geometrically nearest points. A pure distance problem. The most honest approach is called brute force. You compute the distance from the query to every single vector in the store, sort them, and take the 10 nearest. The result is exact, not one-off. But if your store holds 1 billion vectors, each a few hundred dimensions wide, a single query is hundreds of billions of multiply adds, several seconds on one machine. And the user is waiting tens of milliseconds. It's the same story as a database with no index doing a full table scan. It doesn't hold up, and don't count on brute forcing your way through it with a GPU. So the whole of vector search is answering one question. How do you skip scanning everything and still pull out the nearest few? 4 demos, 4 parts, one at a time. The first one, and the star of the show. Approximate nearest neighbor. ANN for short. This is where the whole field's lifeline is hiding. You don't actually need the exact nearest neighbor at all. What you want is close enough, fast. And think about it. The embedding is a fuzzy thing to begin with. It squeezes meaning down into a few hundred numbers and has already thrown information away. Splitting hairs over the first versus the third in a space that Approximate is meaningless. The most common trick is called IVF, inverted file. First, you group all the vectors into piles, clusters. At query time, you only look at the few clusters nearest the query, and you don't even glance at the rest. How many clusters you look at is a knob you can turn. It's called nprobe. I ran it over 8,000 vectors grouped into 128 clusters.
Brute force, 8,000 comparisons per query, recall 100%. That's the ground truth. Switch to IVF. Probe just one cluster, around 200 comparisons, and recall is only 54%. Probe 4 clusters, under 400 comparisons, and recall climbs to 99%. Probe 8 clusters, a perfect score.
Look hard at that trade. Probing 4 clusters, you touch just 5% of the vectors in the store, yet you recover 99% of the true neighbors, 21 times faster. That one bargain. Give up a sliver of recall for an order of magnitude in speed. It's the only reason vector search scales to 1 billion. Exactness was never the point. Close enough, fast is. The other school is HNSW. You build a navigable graph and, from an entry point, greedily hop toward the nearest direction. It's playing the same game. Second part, sharding. One machine can't hold 1 billion vectors, not enough memory, so you spread them across many machines. But there's a counterintuitive trap here. With an ordinary key-value store, you shard by routing each request to the one machine by its key, because you know which shard the key is on. Vectors don't work that way. The nearest neighbor could land in any shard, and you don't have a key that tells you where it is. Similarity can't be carved up by key. So sharding vectors leaves you only one option: scatter, then gather. The query fans out to every shard. Each shard reports its own 10 nearest, and then you merge. I spread 8,000 vectors across 8 shards.
If you copy the key value store in query, just one shard, you save 8-fold, but recall is only 12%. Because the nearest neighbors are mostly in the other 7 shards, and you never even looked. Do it honestly, scatter-gather. Each of the 8 shards computes about 1,000, running in parallel, and after the merge recall is a perfect score.
Sharding does cut the work and the memory on each shard to 1/8, but the price is that every query has to disturb all the shards. Latency equals the slowest shard plus the merge. There's one more detail here. You have to scatter across shards at random. Don't split them by meaning. If you cram all the vectors for one hot topic into a single shard, that shard instantly becomes the bottleneck while the others sit idle. Adding replicas raises your query throughput, but it doesn't get rid of the fan-out. That's the tax you pay for sharding vectors. Third part, incremental updates. ANN indexes have a headache. They're expensive to build and even more awkward to change. You can't cheaply slip a new vector into a tuned HNSW graph. The dumbest way is to rebuild the entire index on every insert. That's n work for each insert, and n inserts makes it n squared, an instant deal breaker. Real systems borrow the LSM idea from the storage episodes. A big, immutable base index paired with a small, mutable delta buffer. To insert, you just append one entry to the delta buffer. Cheap. To query, you search the base and the delta together, then merge. Once the delta piles up, a background job quietly compacts it into the base. Deletes don't touch the graph either. You write a tombstone marker and filter it out at query time. Otherwise, plucking a point out of an HNSW graph would tear the neighbor links apart.
I inserted 4,000 vectors one at a time. The rebuild approach cost 8 million units. LSM cost only 46,000, 174 times less, and inserts never stalled. More important is freshness. I inserted 60 new vectors, querying the base alone. Not a single one could be found, because the base was built before they arrived. Query the base and the delta together, and all 60 turn up, searchable the instant they land.
There's a balance here, too. Let the delta buffer grow too big, and the brute force pass over it at query time gets slow. Keep it too small, and compaction runs constantly, working the background harder. It's the same trade-off as tuning how big the memtable is in an LSM. Exactly the same shape as a right-optimized storage engine. The fourth part, and the deadliest one, filtered retrieval. A real query is never a bare find the nearest vectors. It's find the nearest vectors where the tenant is me, the category is one of these, and the date is newer than some day. Welding a metadata filter onto ANN is where it gets genuinely hard, and whether it works or not comes down to one number: how selective the filter is. 2 ways to play it. Post-filter. You run the ANN search first, then throw out whatever doesn't meet the condition. For a loose filter, that's fine. But once the filter gets selective, the genuinely nearest ones mostly aren't your tenants, so you filter the top 50 and almost nothing survives. You come back empty-handed. Pre-filter. You pull out the ones that match the condition first, then search only within that pile. When the filter is selective, it's perfect. There's so little left that even brute force is effortless. But loosen the filter so it passes 90% of the data and pre-filter degenerates into a full table scan.
I tried a filter that passes only 2%. Post-filter, the top 50 holds, on average, just one from the right tenant, recall 10%, and it looks broken. Pre-filter, searching only within those 160, recall is a perfect score.
Flip it around. Let the filter pass 90%, and the 2 swap places instantly. So the system has to look at how selective the filter is and choose pre-filter or post-filter on its own. That is exactly what a SQL query planner does. It looks at selectivity and decides whether to go through the index or scan the whole table. The fantasy that it's just cosine similarity is exactly where it smacks into reality. The honest card. A vector search system, taken apart, is this: an ANN index, plus a scatter-gather shard router, plus an LSM delta compaction layer, plus a query planner that plans by selectivity, all wrapped around that one embedding function. The part that's actually AI is the single step that turns text into a vector. Everything else is the old craft of a specialized database. Approximate indexing, distributed fan-out, LSM storage, query planning. It's the store RAG scoops passages from, it's the agent's long-term memory, and it has to be served inside the inference service's throughput and latency budget. Old parts again. A few last pitfalls. 1. Don't fixate on latency. The real metric for vector search is recall. Fast but incomplete is a wasted search. 2. nprobe and HNSW's are both knobs between recall and speed. You tune them for your workload. There's no one-size-fits-all value. 3. You need a feel for your filter selectivity, or you either come back empty-handed or degenerate into a full scan. 4. Dimensionality is tied straight to memory. The wider the vector, the more space each one takes, and the harder they are to cluster. Let's wrap up. The vector search machine has that embedding function right at its center, and ringed around it are 4 old parts: approximate indexing, shard fan-out, LSM updates, and query planning. It's the very store the last 3 episodes were all reaching for. The next episode is the Season 3 finale, Designing an LLM Gateway. Semantic routing, semantic caching, rate limiting, retries, and fallback. A front door for everything we've built all season. See you next episode.